Okay, we're recording third hour. Hope you can hear. All right, now hope I can post it somewhere. Anyways, in this activity, I intentionally gave you different syringes for the demonstrators, which ultimately equilibrium should have been achieved where I stopped them if their rate was going forward and backwards. The rate becomes equal, but moles do not become equal in equilibrium necessarily unless you have equal moles. And so I wanted to point that out to you. And the reason I pulled the plug on them doing it is I'm not sure their rate was exactly the same, but it was pretty close. So that this demonstrates to you at equilibrium, moles aren't the same, but the level of the moles of reactant and product would equal out, okay? And so one of the things is, why is it dynamic equilibrium? Why we use that word? Because it's ongoing and it's constant, even though we see no change, okay? Now on the back side of page 1, page 2, there's a question that asks you, what are the limitations to the container demonstration that our lovely classmates showed us? It is, first of all, syncing their timing, making sure that their movement is, the same, so that we are really emulating the rate of a chemical reaction. And if I had not used different syringes with different volume capacities, then you would maybe not understand how moles also are impacted in terms of equilibrium. The mole quantity becomes constant, but not equal. And I'm going to point that out in your lecture notes, but it's an important concept that a lot of times students miss. All right? Under the exercises, this was just to kind of get you to visualize what's it mean to be in equilibrium. So if I have liquid water at 0 and I have ice at 0, what would be going on? Melting and freezing would both be going on simultaneously at an equal rate. You'd see nothing happening, okay? Now that's not what we see when we put ice in water because we don't have them at the same temperature. So you get phase changes due to heat flow. But if you have 0 ice and 0 water, the rate at which ice melts would be equal to the rate at which the water freezes, and it would look like nothing is happening. All right? Number 2 tries to show you this in solution equilibrium in terms of a solid dissolving in solution, and they gave you a molecular solid like sucrose. And here, one thing to note, how do you know it's in equilibrium? Because you see a reaction arrow with a head at the right end and the left end. Or you can do what I do. I just put an arrow to the right, arrow to the left. Either one is adequate. They both mean the same thing. And the implication is these reactions go backward and forward at a constant rate once equilibrium is established. That's what this whole chapter is about. How do you establish that point of equilibrium? How do you predict how much product there will be? How do you predict how much reactant there will be? And how do you look at a reaction and say, is it at equilibrium given quantities in moles or molarity? Okay? If you had this solution of sugar in water and it was at equilibrium, you would have some solid at the bottom. Solid would be dissolving in solution. The solution would be dissolving, would be crystallizing some of the solid out, and it would look like nothing is happening because the rate of the forward and the reverse reactions would be constant. Okay?
This is for concentrated solutions.
Say it again.
Would that be for concentrated solutions?
It would be any solution. Okay? It would be any solution. And generally speaking, guys, we're usually working with ionic compounds in the work that we're going to deal with. All right? This will tie in a lot in terms of Chapter 17, why they chose a molecular. I think they wanted to keep it simple in this activity, just the concept of the rate of the forward and the reverse reaction going back and forth. Okay? All right. And then the third page, what I really like about the third page is, one, it allows you to see how moles are not the same. And so here you have molarity over time. And if you made the graph, you would see for this given reaction, rate does become equivalent right around time 3 when it begins to plateau off, so that it appears that the molarity is not changing. So this is a nice graph to illustrate molarity is not equal left to right in an equilibrium reaction, but rate is equal, and to analyze where it's equal is where your moles start to become stable, and in my mind it was right around time of 3 minutes. Okay? So this little activity really is to just be an introduction to what does it mean to be in equilibrium, since we're going to spend so much time looking at equilibrium reactions. Did I pass out a note packet to you last time?
No.
All right. Any questions on this little activity? Go back to the previous page. Yeah, give me 1 second while people are writing, Gordon.